Okay, well, let's get started today. We do have another announcement that I was asked to share. Another pre-health society, Alpha Eta Alpha, has a meeting next week. I think this is the society, the pre-health society that caters towards non-science majors, but don't quote me on that because I can't keep them all straight. But if you want to find out what they're all about, you can look them up on the web or go to their meeting. It's next week, so that's in the notes as well for you to look at. All right, but we need to plug forward and continue on with what we were talking about last time. So today we're going to move into talking about isotopes and then a whole sort of brand new topic, electromagnetic radiation. But first we need to finish up a couple of things related to atomic structure and some of the early experiments that were done to sort of validate the structural models or find out new information about atomic structure that wasn't known before. So the one we're going to start with is the gold foil experiment. The person who was credited with this is Ernest Rutherford. I don't have a scowling picture of him, but he was around the same time period as the people we talked about last time. All right, Ernest Rutherford. And the idea that this experiment was testing was, if you recall, we talked last time about the discovery of the electron, that there's these negatively charged discrete particles that are in atoms. So, of course, if that's the case, you have to have positive charge somewhere. In the early model of the atom, which we called the plum pudding model, had all of that positive charge as sort of just a diffuse blob that all of the electrons were floating around in. And to test that idea, Rutherford came up with this experiment called the gold foil experiment. And so what he has is an alpha particle emitter. So alpha particles are, you don't need to know much about them, it's just that they're very highly energetic and positively charged particles. They have a lot of kinetic energy. And so the hypothesis, or the expected outcome of this experiment, if the plum pudding model was correct, was that these alpha particles would just pass right through. All right, so imagine taking a BB gun and shooting it at a piece of paper. They kind of thought the same thing would happen here. You have these really highly energetic particles going through a diffuse mass, and they thought it would just bust right through. So the alpha particles were expected to mostly pass through. Maybe they would be deflected a little bit, but this was the idea of what they thought would happen. As is often the case in science, what they thought would happen did not happen. So we'll talk about that here in a second. Alright, so this kind of is a good illustration of the scientific method. They had a model for the atom and they wanted to design an experiment to test that model, and ultimately that model was incorrect because what they found instead was, and this is what the picture shows down here, you had a large portion of the alpha particles did go straight through, but there were a detectable number of particles that were deflected, some of them at very severe angles. Some of them bounced almost straight back towards where they came from. So they were clearly colliding with something very dense and very massive. And so the actual outcome of this experiment was, again, most of the particles went through. However, some were deflected at very steep angles. Or in some cases reflected completely. They went straight back to the source. All right, and then the only realistic explanation for this was that you don't have the positive charge and the mass of the atom sort of diffusely spread throughout the whole atom. The explanation was that the positive charge, remember that the alpha particles themselves are positively charged, so the fact that they're bouncing off suggests that they're colliding with something that's also positively charged, like charges repel each other. And the explanation was that in the atom, the positive charge and most of the mass are all sort of located in a very small volume. And what we now call this area is the nucleus. and then biologists had to co-opt that name for a part of the cell as well. But in chemistry, it's the center of mass and positive charge in an atom. So the new model for the atom that came out of this, still a lot of missing details that we're going to progressively build up over time. But the new model that came out is you have this really tiny, really massive nucleus in the center. And then the electrons are still very diffuse. So there's this diffuse electron cloud. The electrons are not localized in one area of space, or they have a very large volume that they can occupy. And so there's this diffuse electron cloud that surrounds this very dense nucleus at the center. Another way to think about the results of this experiment, which were a surprise at the time, is that atoms are mostly empty space. Alright, the size of the nucleus is extremely small compared to the whole size of the atom, and the electrons are sort of all buzzing around within this cloud at very different locations. So at any given time, the vast majority of the volume of an atom is completely empty. And so even in something that looks like a solid, like a piece of gold foil, there's a massive amount of empty space in there, which is why most of the particles are able to pass straight through. They just go right through that empty space. But there's some that would hit the nucleus here and bounce back, and it's because of that very dense nucleus that you're able to see this. So this was the experiment. This was the way that they explained it. And then so finally we can summarize all the subatomic particles. Now there's one more we haven't talked about yet, which is the neutron. So you had cathode ray experiments, the oil drop experiment, both sort of dealt with discovering the electron. What I just told you about told us that there were protons and that they were also very massive. And then the last subatomic particle that we haven't talked about yet is neutrons. These were actually discovered much later. For a reasonable portion of chemical history, people thought that there was only protons and electrons, and then some more in-depth, complex particle physics experiments later on revealed that there were actually neutrons as well. So let's talk about the difference between these three subatomic particles and where they're located in the atom. So the first important thing is the relative charge. We know that protons have a positive charge. Each proton contributes a +1 charge, if we're talking about it in relative sense. The neutron has no charge at all, so the charge of the atom is not affected by how many neutrons are present. And then the electrons, as we already know, have a -1 charge. So protons and electrons are equal and opposite in charge. If we're going to talk about absolute charge, something we should have been aware of from the review chapter in our book is that the SI unit for charge is coulombs, and an individual proton or an individual electron has a very small absolute charge. 1.6 times 10 to the -19 coulombs for a proton. Still 0 for a neutron. 0 times anything is 0. And then electrons are just the opposite of that, -1.6 times 10 to the -19 coulombs. Now to give you an idea, we work in, the electrical devices that we use in our homes are usually operating on, the scale of amps, which are, 1 coulomb per second is an amp. Each individual electron only has 10 to the -19 coulombs. So when you have electric charge flowing, you have a ton of these particles providing that charge at a macroscopic level. But that's the absolute values. The important thing is that they're equal and opposite for the proton and the electron. Now, as we also talked about, the different particles have different masses associated with them. Protons and neutrons, to a good approximation, I think if you go out to 5 sig figs or so, they're exactly the same. If you go, they're a little bit different from each other, but they're both basically have the same mass. So we would say the relative mass is 1, and the unit that we use for that is AMU. So the mass of a single proton or a single neutron is approximately 1 AMU. That's the atomic mass unit, which we'll use as a convenient form of measurement for individual atoms. And then the electron is much, much smaller than this. So we said most of the mass is in the nucleus, and as I should probably point out before we get too far along, protons and neutrons are both in the nucleus. So those are sort of localized together at that center of very dense mass in the middle. And then the electrons contribute very little to the overall mass, and in general they're ignored when we talk about the mass of an atom. So the relative mass of an electron is an AMU 0.000549. So that's about, what is it, 1,000? I can't do math in my head. Yeah, it's over 1,000 times smaller than the mass. I think it's about 1,800 times smaller than the mass of a proton or neutron. So again, to a good approximation, all of the mass comes from the protons and neutrons. The electrons contribute basically nothing. And then the absolute mass in terms of grams, not that you have to memorize these numbers, but just to give you a sense for their scale, we should recognize that atoms are tiny. And so the mass in grams of a single proton is 1.67 times 10 to the minus 24. To three significant figures, a neutron is identical. If you went out to more decimal places, you would see a difference somewhere. I forget how far out it is. And then the electron is, again, over 3 orders of magnitude smaller than that at 9.11 times 10 to the minus 28 grams. Oh, there's the number that I was trying to do in my head. I have it here. 1,800 times smaller. All right, so those are all of the subatomic particles that make up the atom. And so what we want to start talking about now as we move forward in this first part of today's class is what are the differences between the atoms that make up different elements. So we know that elements are made of atoms. We know that those atoms have to be distinct from each other to give rise to those different elements. And so how are they exactly distinct from each other, and how many of these subatomic particles do each of them have? So let's start with talking about atomic symbols, which is how we identify elements and how we identify the properties of the atoms that make up those elements. The first thing we should realize is what distinguishes one element from another. The only thing you look at is the number of protons in the nucleus. So that is sort of the identifying feature of an element, is how many protons are in the nucleus. So that tells you what element you're talking about. And then from there we can write a symbol for each type of atom that we're interested in that has the basic anatomy that looks like this. So you have a symbol in the middle, and then you're going to have a subscript and a superscript on each side. So that'll be abbreviated A, this will be abbreviated Z. So you write two, these are both numerical quantities that you're going to write to the left of the symbol. And let's define what all those mean. Alright, so X is the atomic symbol. And it's a 1 or 2 letter abbreviation for the element that you're talking about. And if you want to, when you're writing out atomic symbols, if you want to look like you know what you're doing, make sure you only capitalize the first letter, and always capitalize the first letter. Okay, so that's the atomic symbol, and so each element, all 118 of them now, have a symbol associated with them. I think they've gone to 3-letter symbols now for some of the new ones, the ones that I said only persist for picoseconds or whatever at a time. But most of the common elements, or the ones that are naturally occurring anyway, have 1 or 2 letter symbols. And as you saw when you were studying for your PA test, you are required to know the names and symbols of the first 36 elements. You don't need to know what order they come in, but keep in mind the periodic table that you use on the test only has the symbols on it, so you have to know what element that corresponds to. So spend some time learning that if you're a little bit rusty on it. Now the other parts of the atomic symbol that tell us some information about the atom itself, this one on the bottom here is Z, and that's what we call the atomic number. And this is equal to the number of protons in the nucleus. We'll start using the abbreviation P plus for protons, in case that confuses anybody. Right, so the atomic number is just the number of protons in the nucleus. As I said, that's characteristic of the element. And then finally, A is the mass number. It's a whole number. And it's the number of protons plus the number of neutrons in the nucleus. Okay? So this is how you identify an atomic symbol. It's going to have at most 3 parts to it. The symbol, which tells you what element it is, the number of protons, and then the mass number, which is the sum of protons and neutrons. Now what you can sometimes have is what are called isotopes. So not all atoms that make up an element are identical to each other, and this is what the idea of isotopes is. So what is the definition of isotope? It's atoms of a given element. Now keep in mind, if we're talking about one element, that means all these atoms have the same number of protons in them, but they have different masses because they have different numbers of neutrons. So isotopes, the only difference between an isotope, between one isotope and another, is the number of neutrons. Differ in the number of neutrons. And because they have different numbers of neutrons, they have slightly different masses. Because remember, that mass number, which is the approximate mass in AMU, is the sum of protons plus neutrons. So if you add or subtract neutrons, you're going to change the mass. And this is the one part that Dalton was wrong about in his atomic theory. So remember that part of the atomic theory, which was developed way before we even knew isotopes existed, part of the atomic theory was that all atoms that make up a given element have the exact same mass. And that's not entirely true. You have, in most cases, for most naturally occurring elements, you have more than one isotope, which is more than one type of atom that can make up that element that has different numbers of neutrons in the nucleus. So there are some elements that only have one naturally occurring isotope, but most of them have more than one. And so let's talk about the properties of isotopes. Now, the reason that people didn't even recognize isotopes existed for a long time is because the properties of two different isotopes of the same element are basically identical. Okay? So as we'll learn in this course, most of the chemical properties are a function of the number of electrons and the locations of those electrons and things of that sort. So the nucleus doesn't really contribute to the chemical properties of an element. So if you have isotopes for a given element, they're going to have almost identical properties. Their chemical reactivity will be the same, their melting point, their boiling point, any physical property you can talk about. If you have two isotopes of the same element, they're going to have nearly identical properties. Which means it's often difficult to separate isotopes, but that's a story for a different day. But the properties are not very different from each other. They're just by adding or subtracting neutrons from the nucleus, you don't change things. Now, a common example, or perhaps the simplest example of isotopes, would be hydrogen. So many of us know already that hydrogen is the smallest and simplest, smallest element on the periodic table, the simplest atom that you can imagine. So if we write the atomic symbol for hydrogen, the symbol is H, and then hydrogen has one proton, and the most commonly occurring isotopes, are going to put a 1 down there for the number of protons, and the most commonly occurring isotope has 0 neutrons. So actually the hydrogen nucleus is the only one that doesn't always have neutrons in it. This is the most abundant form of hydrogen, and it has 0 neutrons in the nucleus. So this isotope of hydrogen has 1 proton and 0 neutrons, and that's the one that's most commonly occurring. There is a small percentage of what's called deuterium, which is a different isotope of hydrogen. So the second isotope of hydrogen, which occurs in a very small quantity, but it is naturally occurring, is deuterium. And that's going to have this symbol here. So still, it's hydrogen. It must have 1 proton in the nucleus. You can't change the number of protons in the nucleus. You have a different element. But it has 1 more neutron, so the mass number goes from 1 to 2. So this is 1 proton, 1 neutron. And then finally, another isotope of hydrogen, which is very valuable for biological studies, is called tritium. Now, tritium is not naturally occurring, as far as I know, or at least not in detectable quantities, because it is radioactive. But it's used in biological studies because you can trace it very easily because of its radioactivity. But anyway, the difference here, of course, is now we have 2 neutrons in the nucleus, still 1 proton, but now a second neutron that gives us a total mass number of 3. So these are the 3 isotopes of hydrogen that have been identified, and like I said, most elements have 2 or more isotopes that differ in the number of neutrons. Hydrogen is the one case where the different isotopes do have fairly different chemical properties because of how small hydrogen is. So think about it, we're going from hydrogen 1 to hydrogen 2 or deuterium, we're doubling the mass. That's a pretty big dramatic change. For most elements, if you add 1 neutron, you don't change the mass by all that much. The consequence of that is we should recognize, our body has a ton of water in it, and a lot of the food that we metabolize, this is just a side story, you don't have to worry about this, but I think it's fascinating. Anyway, look, we have a lot of hydrogen in our body, we have a lot of things that we eat have hydrogen in them, and because deuterium is so much heavier than hydrogen, if you were to replace the hydrogen in your body with deuterium, your metabolism would slow down to the point that you couldn't survive anymore. And I think if you drink somewhere on the order of half a liter of deuterated water, you put yourself in severe danger because of that, because it basically replaces all the hydrogen with deuterium in your body, and it slows down your metabolic processes because deuterium is twice as heavy as hydrogen. So many people think that, I don't know if I should give you this advice, but one of the best ways to off somebody is to give them a deuterated beverage where that replaces the deuterium, and their hydrogen in the body with deuterium is virtually indetectable unless you know to look for it. So, but it can cause some severe damage. But I wouldn't recommend trying that. Please don't. I give bad advice sometimes, and that's one of those things. All right, moving on though. So that's a quick summary of isotopes. Let's do a couple sample problems about isotopes. Going to a heavier example, palladium, PD. This is not one you'd have to memorize the symbol for because it is beyond atomic number 36, but it's called palladium. And we're going to know the number of protons, electrons, and neutrons in the two most abundant isotopes of palladium. So again, we just have to look at the atomic symbol that's given to us and be able to identify what the different parts mean. Okay, so remember that this bottom number here tells us directly the number of protons. This top number here is the number of protons plus neutrons. And so we can quickly identify that the number of protons is 46, and that would be true for any isotope of palladium. In this case here, palladium-106, this has a mass number of 106. We just have to do a quick piece of algebra to find the number of neutrons. It's just going to be the mass number minus the number of protons. So we have 60 neutrons in this isotope. 46 plus 60 is 106, which is the given mass number. And then finally, the one I haven't talked about yet is the number of electrons. We've kind of already mentioned, though, if you have an atom that has no charge associated with it, you must have equal numbers of protons and electrons to cancel out those positive and negative charges. And so if you don't have charge, you just have to say the number of electrons is going to be equivalent to the number of protons. So in this isotope, it would also be 46. For any time you have a neutral atom, no charge is indicated here. And then same song, second verse. If we talk about this other isotope of palladium, the only difference again is the mass number when we're talking about two different isotopes. It's the same element, so we don't even have to do any work. We know that the number of protons and the number of electrons stay the same element, no charge involved, so it's still 46 protons, 46 electrons. But the only difference here is that the number of neutrons changes. We've gone from a mass number of 106 to a mass number of 108. And so if we subtract the number of protons from that mass number, we see that there is now 62 neutrons. And as a percentage of total mass, this isotope is only 2% heavier than that one. So you can imagine that has a much smaller effect on the properties compared to hydrogen, where you're doubling the mass. But anyway, this is just another example of isotopes, and these are the kinds of problems that you probably already saw in the PA test if you took it, and then you will see them again on the homework and things of that, so get practice with those. All right, finally, one more sample problem just to make sure we understand how to write atomic symbols. We have a fictitious element with the symbol Q. There are no elements with the symbol Q. You can try to find one, they're not there. And this element has 34 protons and 43 neutrons. Write the proper atomic symbol. So here we're just working backwards from what we did before. So the atomic symbol is, again, in general form, the symbol in the middle, the Z, which is the atomic number at the bottom, and the mass number at top. Okay, so Z is the number of protons, and we're told in this example that there are 34 protons, so that's going to be the number we put down there. And then the mass number we're not directly given, but it's just a sum of two numbers. Hopefully we can all add. And it's going to be the number of protons plus the number of neutrons. 34 plus 43 is the number of neutrons, and we have a 77. All right, so then when we write the symbol, we put the symbol Q in the middle. We put the atomic number at the bottom, the mass number at the top, and there you go. Now, obviously, we can't ask you to do this in Blackboard, but you should still know how to write an atomic symbol. It's not that difficult to write, but in Blackboard, these would be more multiple choice type questions, obviously. All right, so that's the atomic symbol for this pretend element. Now, the last thing I want to talk about, we're going to, we haven't talked about the periodic table yet, and we won't talk about it in detail just now. But actually, no, I skipped ahead of myself. Sorry. We're going to talk about ions first before we get to something about the periodic table. Please, I may have forgotten a page of my notes. Here we go. I might have to fly blind. Okay, so let's talk about ions for a second. So everything we've talked about in those last few examples were neutral atoms, meaning equal number of protons, equal number of electrons, and no net charge. But sometimes, and so that's true for any neutral atom. So equal numbers of protons and electrons to balance the charge. Okay, so that's true for neutral atoms, but then if we have an ion, which is something that has a net positive or net negative charge, the way that we can, when we're counting subatomic particles, all we're doing when we form ions is removing or adding electrons. Okay, so the only subatomic particle that we're ever going to add or remove when making a charged species are the electrons. Okay, it's tempting, and some people make this mistake, which is you never want to add protons or remove them from the nucleus. And that should be clear why that is based on what we talked about, which is this: by doing so, you would change the identity of the atom or the element. So you never touch the nucleus when you're just forming ions. And in fact, when we're talking about 99% of chemistry and 100% of the chemistry that we'll learn about in this course, all that's involved is moving electrons around. Adding electrons, removing electrons, moving electrons from one thing to another. You never touch the nucleus whenever you do chemical reactions. You guys will learn a little bit about nuclear chemistry in Chemistry 2, but that's probably the last thing we'll talk about, so it's quite a ways away from now. So we never remove protons or add them, because that would change the identity of the atom. And obviously what you want to do, we know that the relative charge of protons and electrons is the same in magnitude, opposite in sign, and so you're just going to add one electron for each negative charge that the ion has. So ions can have, more than one charge potentially. So for each negative charge, you just add an additional electron and you subtract one electron for each positive charge. All right. So any questions on that? That's pretty straightforward. Let's just see some examples if there's no questions. So let's look at two atomic symbols. And if you have a charge, this is something I didn't talk about yet, the charge is going to be indicated to the right of the symbol. And it has to be designated as plus or minus, so you know whether it's positive or negative, obviously. And again, we still put those two other numerical parameters to the left of the symbol. So if you have a charge, it's going to be written to the right. That's how you know that you're talking about an ion and not an atom. The first one here, again, not a symbol you'd have to know off the top of your head, but this is called iridium. It's my favorite element on the periodic table. Most people have favorite singers and favorite movies. I have favorite elements. And anyway, if we want to ask, the question that's asked here is how many protons, neutrons, and electrons are present in these ions. So the number of protons, the number of neutrons, we do exactly the same way as before, because again, the identity of the element is going to dictate how many protons there are. That's this number down here, and then the mass number is still given, and it has the exact same definition as it did for a neutral atom. So the number of protons is just this 77 down here, and then the number of protons plus the number of neutrons is equal to the mass number, which is 192. That's that number there. And so we're not doing anything differently to find the number of neutrons and protons. So this would just be 192 minus 77. So you have 115 neutrons in the nucleus. Now the only thing that's a little bit different here is that we have a net charge. So when we're figuring out the number of electrons, we have to account for that. So we have 77 protons, and if we're going to have a plus 3 charge, that means we need to have 3 fewer electrons than that. And that'll leave us with a net plus 3 charge. So remember, in a neutral atom, there's equal numbers of protons and electrons. If you have a positive charge, you have to take away some electrons. So in this one, we need to remove 3 electrons, which means we decrease the number of electrons by 3, and this would have 74 electrons. So when you're forming ions, the only thing that's different is the number of electrons. And then same thing for a negatively charged ion, sulfur 2 minus, sulfide. Again, we look at the mass number and the atomic number, which are given on the left, to find the number of protons, which is 16. And then the number of neutrons, which is that mass number, 33 minus 16. So we have 17 neutrons, 16 protons. And then to find the number of electrons, we have 16 protons. The neutral sulfur would have also 16 electrons. We have 2 additional negative charges in this case. So that means we have to add 2 more electrons to get a net negative charge, which means we need to have 18 electrons. All right, so positively charged ions have fewer electrons than protons. Negatively charged ions have more electrons than protons. And it's this that accounts for that negative 2 charge. All right, so that's only a little bit of a slight wrinkle that you just need to keep in mind when you're counting the number of electrons if you have something that has an overall charge. So any questions on how we do that before I move on? Okay, so the last relevant topic is going to be using the periodic table to help us find the number of protons. So this is what your periodic table entries are going to look like vaguely. I think it's pretty close to this. But anyway, what you have is the atomic symbol in the center. So that's the symbol that would go at the center of the symbol. The 1 or 2 letter one here is carbon, which is just C, capital letter. And then if you look at how our periodic table is arranged, this number up here, which is always a whole number, this is the atomic number. Okay, so you're always going to have the periodic table in front of you, so you can use it to help you determine the atomic number if it's not given to you directly. Which again, this is the number of protons, and that identifies the element that we're talking about. This number down here we're not going to talk about in great detail right now. This is related to the mass number, but not exactly equal to the mass number, and you'll see that it's not a whole number in most cases either. So this is related to the mass number, but we'll define it more precisely later. So and this won't tell you the mass of an individual isotope. So this is a sort of a collective mass of all the isotopes, as we'll see. So if you want to know the mass of an individual isotope, you do need to know the exact number of neutrons for that isotope. Now the reason I'm pointing this out now, or another reason to point this out now, is that very often in atomic symbols you don't include the atomic number. So that number that I abbreviated as Z, the atomic number, is usually going to be left out of atomic symbols. And the reason for this is if we write the symbol for the most abundant isotope of carbon, which is carbon 12, carbon has an atomic number of 6, which we saw up here, that number above the C. This is the most abundant isotope of carbon. Every isotope of carbon will have 6 protons, so it's kind of redundant to also write the 6 down there if you have the symbol for carbon right there in the middle. So there's no reason to include it in most cases. A lot of times you'll see this just written as carbon with the 12 there, and not including the atomic number, because the fact that the symbol is C tells you that it's carbon, which tells you that it has 6 protons. You don't need to have both of those pieces of information. They're dependent on each other. So this is the more common way to write atomic symbols. You'll probably see this on the homework assignments quite frequently, so don't be confused by the fact that we often leave out Z, because Z is redundant with the symbol that's present there. Okay, so that's sort of the story of how we use the periodic table to help us find the number of protons and an alternative way of writing. Obviously, if there was a charge involved, you'd still put that on the top right, so you can include charges still, but this bottom left is usually left blank in most cases. All right, so let's just close with a couple more sample problems related to isotopes. So we're going to determine which 2 plus ion has the same number of electrons as Br minus. All right, so kind of a convoluted question. And for here, we're going to need to use the periodic table to help us, because we're not giving you the full atomic symbol for bromine. We're just telling you that it's Br minus. So we need to figure out from the periodic table how many protons does that have, and then use that to figure out how many electrons it has, and so on. And so if we talk about Br minus, the atomic symbol tells us the identity of the element, and we're going to need to go to the periodic table to find that. So let me pull up our periodic table. This is the one that we use. And I think hopefully the people that are following along on YouTube who skipped class can see the pointer that I have here to address the common complaint that people can't see what I was pointing to because they're so high maintenance they can't just watch the videos, they have to. Anyway, so if we go down and find Br, atomic symbol for bromine, let's zoom in because it's a little bit small for you guys. There it is, atomic number 35. And it'll maybe eventually, maybe it's going to be pixelated because this is not a very high resolution file. Alright, that's better. Bromine 35, so that tells us that it has an atomic number of 35, which means it has 35 protons. There we go. 35 protons, and it's Br minus, so that means it has to have one extra electron. And so this has 36 electrons. So that's what we're starting with. We want to determine which 2+ ion has this same number of electrons. Okay, so if we want to find a 2+ ion that has the same number of electrons, 36 electrons also, how many protons does it need to have? Okay, 38. Does everybody see why that is? We have a 2+ charge, that means we have to have 2 more protons than we have electrons. We want to find the 2+ ion that has 36 electrons, means it has to have 36 protons. And then figure out which element this corresponds to. We have to go back to the periodic table and find atomic number 38. This is not one of the ones you would memorize, but you should be able to find the symbol on the periodic table because they're arranged numerically. So if you can count, you can find this. And so 38 is right here, Sr. The name for that is strontium. And so if you had strontium with a 2+ charge, you would have 38 protons, also 36 electrons, same number as Br minus. Alright, so this is called Sr2+. And we'll talk in a lot more detail about the number of electrons and the electron configurations for ions, but for now you should be able to at least identify which ones have the same number of electrons as each other. A terminology you might hear me use or see is that species that have the same number of electrons are called isoelectronic. Iso means the same or equal. Electronic, of course, means number of electrons. So these would be considered isoelectronic ions. They don't have the same charge, but they have the same number of electrons. That's what identifies them as being isoelectronic. Alright, and then finally, let's say we do a little bit of nuclear chemistry. Again, you're not going to talk about this in detail until Chemistry 2, but we have the knowledge to at least answer some simple questions like this. So let's say we have a 207 lead 2+ ion. That loses 2 protons and 2 neutrons. Now this combination of 2 protons and 2 neutrons is what we call an alpha particle. That was what was used in the gold foil experiment that I introduced at the beginning. So an alpha particle is just 2 protons and 2 neutrons glommed together that can have a lot of energy if they're projected at a target. And so anyway, this ion here loses an alpha particle, loses 2 protons and 2 neutrons, and we want to know what is the name of the new the atomic symbol for the atom that results from this. Okay, so let's figure out how this works. So what we have to first figure out is how many protons we're starting with, because we're losing 2. We need to know how many we started with. And I didn't tell you that directly because, once again, the atomic symbol is directly relevant to the number of protons. So we just need to find Pb, which is lead, on the periodic table. So if we go back to our periodic table, lead is over here, atomic number 82, one of our heavier naturally occurring elements. And so it's atomic number 82, which means that lead will have 82 protons in the nucleus. That's what we're starting with. So the full symbol would have an 82 down there. Again, we don't always write that, but that's the full symbol. And so this starting ion that we have has 82 protons. We need to find the number of neutrons that we're starting with. So remember, the number of neutrons is just, you subtract the big number from the small number below it. So 207 minus 82 gives us the number of neutrons, which is 125. the sum of these two numbers is 207, the mass number, of course. And this is a 2 plus ion, so it has 80 electrons. Because if we're going to identify, we need to identify the charge of the species as well at the end. So we have, these are the subatomic particles that are present initially, and then we're saying we do some sort of a hypothetical nuclear reaction where we lose 2 protons and we lose 2 neutrons. All right, as I said, if we do nuclear chemistry, we are going to change the identity of the element. So we lose 2 protons, so our new atom that we're forming, or new ion as it may be, we'll figure that out later. The new species that we form has now 80 protons. We've lost 2. We've also lost 2 neutrons, so it has 123. And we didn't say anything about the electrons, so we'll assume that it kept all of its electrons and still has 80. So our new species has 80 protons, 123 neutrons, 80 electrons, and now we just need to use these numbers to build the new atomic symbol that we have. So our new atom is, if we go to the periodic table, we need to find the element that has 80 protons. So we were starting with 82, we lose 2, we get to atomic number 80, which is Hg, which intuitively is mercury. Not intuitively, but that's not one you have to memorize. But this is mercury. Hg is the symbol. That's all we asked for. So Hg is the symbol. We don't necessarily have to write the 80 down there, but we could if we wanted to. And then finally, if we want to know the mass number that goes up here, we have to add these two numbers back together. 80 plus 123. So the new mass number is 203. Or an alternative way to think about it is we started with a mass number of 207. We lost 2 of each, so we lost 4 mass units. Takes us down to 203. And then if we think about the charge, whether this has a charge or not, we now have equal numbers of protons and electrons, 80 of each. So we've also lost our 2 plus charge. And so this would be our final answer, just 203 Hg, that isotope of mercury. So we won't talk in detail about nuclear chemistry, but it is possible to convert one element into another if you're able to add or remove protons and neutrons from the nucleus, which in some certain situations you can, but it's not a very easy thing to do. Okay, any questions on isotopes before we kind of switch gears here abruptly into something totally different? Okay, so let's move forward. Now, it's gonna seem weird that we're talking about this. A lot of you are going to be like, "This is a physics topic. Why do I care about it in chemistry?" And why do I care about it at all? Now, the reason we care about it in chemistry is because we've talked now about the structure of atoms at a very simplistic level. We know we have protons and neutrons in the nucleus. We know we have electrons that are sort of floating around the nucleus, but there's a lot of details we don't quite understand yet, which is, how are those electrons arranged around the nucleus? Are they all exactly the same distance from the nucleus? Are they all freely moving about wherever they want to be? How are the energy levels of those electrons? Are those energy levels any old value you want them to be? Are they discrete energy levels? There's a lot of details about the electrons, the important part of the atom from a chemistry standpoint, that weren't really well understood at that time in the early 20th century when a lot of these ideas were formulated. And so what came about and what we're going to work into is by studying the interaction of electromagnetic radiation with chemical elements and chemical compounds, people were able to learn a lot about the electronic structure, or in other words, the arrangement of the electrons in atoms. So it's really those interactions between light and matter that were critical for developing a more sophisticated picture of electronic structure that we're going to work into now. Now, I want to give you a fair warning. For those of you that have the textbook, which is not all of you, but if you do, you'll notice that the title is called Atom's First Approach. And so the idea of the Atom's First Approach, as the name implies, that we're going to learn all of the nitty-gritty details of atomic structure first before we start looking at ensembles of atoms and chemical reactions and things like that. So these are traditionally some of the more conceptually difficult topics for Chemistry 1. They're mathematically not too bad. As you'll see, we don't have too many problems that involve high-level mathematics, but conceptually they're kind of difficult. So you want to make sure you're on your A game as we learn this, and keep in mind that these are difficult concepts, but ones that I think you'll be able to understand as you go through them. But they require us to first have an appreciation for electromagnetic radiation, because we're going to talk about the interactions of electromagnetic radiation with atoms, and so we need to understand what these electromagnetic radiations are and some of their key properties. Okay, So an electromagnetic wave, which the term wave and radiation are kind of used interchangeably. So what exactly is it? We have energy that's being propagated by electric and magnetic fields that oscillate. And they oscillate in intensity as they travel through space. Okay, so they're electromagnetic fields that oscillate in intensity as they travel through space. So what the wave, then the fields are perpendicular to each other. So what the wave would sort of look like is, as this one is drawn, the blue wave is the electric field oscillating, and then at a 90-degree angle to that you have a magnetic field that also oscillates. Now what I mean by oscillates means it goes up and down in intensity. So this is what a standing wave would look like. If you could imagine standing somewhere and watching sort of a frozen snapshot of a wave moving through space, or sort of a time-resolved photo of that, this is what it would look like. Alternatively, what you can think of as an oscillating wave would be, imagine that you're standing in place and one of these waves is going in front of you and you're able to see the changes in intensity. You would basically have the magnetic and electric fields would be going up and down at some frequency with respect to time. Okay, so that's what we mean by oscillation. They're regularly repeating in higher and lower intensity as a function of time as they move through space. All right, so what are some examples of electromagnetic radiation? You guys all know what these are. You've all seen them in your daily life. So visible light, the reason that we can see anything is because of electromagnetic radiation. And then there are other forms, X-rays, so if you've had medical procedures done, radio waves, microwaves, and so on. All right, so these are all different forms of electromagnetic radiation. And the difference between all of these different forms of electromagnetic radiation are really two key properties that, as we'll see, are very much related to each other. So the two key properties of a wave that are important to us are frequency and wavelength. Okay? Okay? And we're also talking about the abbreviations for these. So frequency has a Greek letter abbreviation which is called nu. It looks like a V that has a hurricane force wind sort of blowing on the side of it. Anyway, you're going to learn some Greek letters in this course. You thought you were just here for chemistry, but you're also going to learn the Greek alphabet. And this is the first one we'll see, nu. So don't call it V or I'll get upset. And so this is how we abbreviate frequency, and this is the number of cycles or oscillations per second. The unit for that is called Hertz, Hz, named after a scientist, Hertz. And so it's the number of cycles per second. So again, imagine if you're standing in place watching one of these waves travel in front of you, it would be the number of times in 1 second that the intensity goes up and down. Okay? So that's the frequency of the electromagnetic radiation. Let me change my color? Maybe not. Sometimes the tablet takes a break, so periodically we'll have pauses. There we go. All right, and then the one I'm going to do in a different color so I can illustrate it better. Just processing. This is fun. Okay, let me try to close this and open it back up. The other thing I can do, I think, is Alright, when in doubt, restart. It's about the halfway point, so I guess it's a good time to take a little breather anyway. I just wish that I was dictating the terms of this breather, not my tablet. Next question, is it the pen? Maybe it is. Alright, I think we're back, so break time's over. Alright, so then the other parameter of a wave that we're going to talk about, the other property, is wavelength. And this has the abbreviation lambda, another Greek letter. And this is the distance, the linear distance between equivalent points in a wave. Okay, so that's frequency and wavelength, and then the last property, which is not that important, so maybe I should just get rid of it and not tell you about it anymore, is what's called amplitude. This one has a nice regular Roman letter abbreviation. Amplitude A, which is the height of the crest. And this is not going to factor into most of the things we talk about, or really any of the things we talk about in this course. But you can think of it as the intensity of the electromagnetic radiation. So if you had, if you had a simple light bulb, you would have relatively low amplitude. If you had a laser instead that had much higher power, the amplitude of the wave would be much bigger. At least that's how it's thought of classically. But let's illustrate some of these things on here. So starting with amplitude. Amplitude, as I said, is the height of the crest, which means it's the distance from the midpoint of the wave to the top. Alternatively, you could think of it as the distance from the midpoint to the bottom. Those are the same because these oscillate symmetrically. So that's how we would abbreviate or label amplitude. And then the other two are frequency and wavelength. Now when you look at a picture of a wave like this, what we call a standing wave, there are two ways to interpret the x-axis. They can either be interpreted in units of time. So in other words, as time goes on, this is how the amplitude of the wave oscillates as a function of time. So if we interpret the x-axis as time, then that tells us what that can allow us to determine what the frequency is. So for this wave here, let's assume that this full scale here from this first peak to the last one, let's assume that that's equal to 1 second. I didn't put the scale on here, but let's make that assumption now. If this is 1 second, we want to think about how many total cycles of this wave do we go through in 1 second. So we start here at the top, we go, that's one cycle back to the top. That's a second cycle, third cycle, and a fourth. Just breathe again. And so if that's 4 cycles in 1 second, that would tell us that our frequency is 4, which can be written as inverse seconds, or more commonly 4 hertz. So if we define this time scale as 1 second, this wave goes through 4 cycles in 1 second. It means it has a 4 hertz frequency. And then if we want to define the wavelength lambda on this plot, it's the distance between two equivalent points on the wave. So there's a lot of different ways we could measure lambda. So if we go from one peak to the next, that distance there, if we interpret the x-axis in terms of length, that would be lambda, the distance between those two. Or alternatively, we could go from the midpoint of the wave, the node, all the way through to the next node, and that would also be the same distance, lambda. Or from the bottom to the bottom is also lambda. So there's a lot of different ways to think about wavelength, lambda, but it's just the distance between two equivalent points on the wave, and no matter which two equivalent points you choose, you're going to get that same distance, lambda. All right. So let's talk a little bit about the relationship between wavelengths and frequencies. So let's look at what happens when we change one or the other. So we have two waves here. Wave A is shown in blue, wave B is shown in red. And so let's look at the relationship between the wavelengths of these ones. So if we count the number of units for the wavelength of A, we go from this point here to another equivalent point there. If we count how many divisions there are between here, it's kind of probably a little bit faint. You can see it if you look closely. You have 1, 2, 3, 4, 5, 6, 7, 8. So in whatever unit this is given in, this distance here for lambda A is 8 as a unitless quantity. And then if we look at the frequency for A, if we count how many cycles there are over a given period on this graph. So if we count the number of cycles for A, in this, from here to here, we go through 1, 2 cycles. So 2 cycles for the first wave A. Let's compare that to the second wave B, as we've labeled it the red one. And so if we look at B and we measure the wavelength for B, we count the number of divisions between those two crests. There's 4 in this case. So the wavelength for B is 4 on whatever scale this is. And then if we count the number of cycles for B, we start again at a crest up here. We go through 1, 2, 3, 4 cycles in whatever unit of time that axis represents. And so if we compare the wavelengths and the frequencies of these things, what we see is that the wavelength for the first wave is 2 times the wavelength for the second. Lambda A is 8, lambda B is 4. But if we compare the frequencies, nu A is 1/2 times nu B. So you see that there's this inverse relationship between wavelength and frequency. If the wavelength is doubled, the frequency is half, or vice versa. Okay, so that's what we call an inverse relationship, and that'll be important later on when we start giving equations for these different things. And then finally, the last thing about amplitude. As I said, amplitude is not terribly important, so I don't want to spend a lot of time on this. So let's just go through it quickly. If we look at wave A, which again is in is in blue here, if we identify the amplitude for wave A, remember that's from the midpoint to the top, so I think I drew that wrong. It should be from the midpoint of the wave to the top, which is this position here to the top. That's 2 divisions, as I have it on the vertical scale here. This one doesn't show up very well on the screen, but you can see 1, 2 divisions. And then finally for the second wave B in red, that would be 1. So it has half the amplitude. And as I said, the only physical significance of this is that if you talk about whatever electromagnetic radiation these waves represent, A is either brighter or more intense than B. Alright, so if this was, for example, the light that was given off by a light bulb, and these were the wave profiles of those two, wave A would be a brighter light bulb than wave B. And that's the only physical significance of that, and we're not going to talk at any real quantitative level about amplitude, but just be aware of what that means. So moving on then, let's talk about more of the relationship between wavelength and frequency. So we saw that they're inversely related already, because if we saw that if the wavelength went up by a factor of 2, the frequency went down by a factor of 2, and that was the example we saw, but any inverse relationship like that would happen. So if we want to write that mathematically, that means the wavelength is inversely proportional to frequency, which you can write as lambda is proportional to 1 over the frequency. So whenever things are inversely related to each other, This is the proportionality that you establish. And a common trick that we're going to see when we derive formulas in this class, this is not a particularly complicated one, is that if you have two things that are proportional to each other and you want to change that proportionality to an equal sign, you just have to multiply one side by a constant of some sort. Okay? And so the way we write this as an equality is that lambda is equal to a constant c divided by nu, c divided by the frequency, or alternatively the product of the wavelength and the frequency, nu times lambda, is equal to that constant c. Alright, and then we should all know what c is. C is the speed of light. So if we have the product of wavelength and frequency, that gives us the speed of light, which in a vacuum, which means no medium present, no air or water or anything present, that's 3 times 10 to the 8th meters per second. Okay, so if you take the product of these two, it will always equal 3 times 10 to the 8th if you're dealing with a vacuum, where it's very close to this number if you're in just air, regular atmosphere. Now you don't have to memorize that number because it is on the periodic table, which I closed to. So at the bottom of your periodic table, if you haven't looked at it yet, you have a list of constants down here, and there you go. The very bottom one is the speed of light, which is 2.99792, close enough to 3. Times 10 to the 8th. So it's right there. You don't have to memorize it, but I guarantee you'll do enough problems that you will memorize it even if you don't want to. Okay, so that's the speed of light, 3 times 10 to the 8th. And so there's this inverse relationship between wavelength and frequency in the way that we classify different types of electromagnetic radiation is by their relative wavelengths and frequencies. So this is the scale that you'll want to commit to memory that has the different types of electromagnetic radiation ordered in terms of their wavelength and frequency. So as we go from left to right, this is increasing wavelength. So the wavelength is getting longer as we go from left to right. So gamma rays have the shortest wavelength, and then X-rays are next. And then you have ultraviolet, and then visible, infrared, microwave radio. So that's the order that they come in terms of wavelength. And then frequency would be the opposite. So the frequency, as you can see, increases from right to left. So gamma rays have the highest frequency, and radio waves have the lowest frequency. Okay? So, and then if we look at this very thin slice of the electromagnetic spectrum that corresponds to the visible range, that corresponds to the wavelengths of about 400 to 750 nanometers is the wavelengths of light that we can see. So I'll write that a little bit bigger so you can see it better. So the wavelengths are about 400 to 750 nanometers. That's being generous. Most people can't see much beyond 700, but 750 is one arbitrary cutoff for the visible spectrum. And this is your typical Roy G. Biv spectrum that you guys all learned about back in 5th grade. So red, orange, yellow, green, blue, violet, and so on. So that's the order that they come in. Increasing wavelength is blue to red, increasing frequency, red to blue. So this is the electromagnetic spectrum, and this is how we classify the different types of electromagnetic radiation. So you'll want to know the relative orders of these. You don't need to know the numbers or the numerical divisions of them. But you should know the order that they come in. All right. So let's do a couple sample problems involving waves. So let's say we have 600 nanometer light, which is orange in color. We want to know what is the frequency of that. So the equation that we're going to use anytime we're converting wavelength to frequency is this one here. Frequency times wavelength equals speed of light c. And so if we want to solve for the frequency, we just need to divide the two, do a little bit of algebra. So frequency is c divided by lambda. And the one part of these problems that we have to be careful with, because people don't often think about units, we have to be very careful with units. And you guys are going to get sick of me talking about units in this course, but they're very important and they help you get questions right, which I think you all want to do. Because very often the only mistake that people make is putting the wrong units in. So don't let that happen to you. So if we look at the units for this problem, we have the speed of light is always given to us in meters per second, so there's no reason to convert it to anything else. But because our speed of light is in meters, we have to put lambda, the wavelength, also needs to be in meters. Remember that lambda is measured in units of length. And so in order for these units to divide out properly, we need our denominator to also be in meters. So we have to do a little bit of conversion here. And so you're going to need to know your prefixes for different metric units. So we have a wavelength of 600.0 nanometers. And what you have in your book and what I've reproduced in the notes for you is this table here that tells you all of the prefixes, especially the ones that go from, I would say, tera down to pico. You should probably know, okay? So you don't need to know, maybe the very first couple and the very last couple are too big and too small to really commonly encounter them. But the ones that we'll see a lot in this course are tera at the top, pico or nano at the bottom. And so if we look at nano, nano is 10 to the minus 9. Okay, so that means that 1 nanometer is 10 to the minus 9 meters. Or alternatively, if we want to convert from nanometers to meters, 1 meter is 10 to the 9th nanometers. You can write that in either way. But we want meters on top, nanometers on the bottom, so that the units cancel out properly. And this gives us a wavelength of 6.000 times 10 to the minus 7 meters. So we need to put it in with that quantity. So that our meters cancel out and we're left with just inverse seconds, which is hertz. And so when we plug the numbers into our calculator, we get... Also, make sure you practice with whatever scientific calculator you're going to use, because every scientific calculator has slightly different syntax for exponential quantities, and starting right off the bat, we're going to use a lot of those exponential scientific notation type quantities, so make sure you know how to do that on your calculator. So this comes out to 5.000 times 10 to the 14th hertz. If we wanted to write it in a little bit more of a convenient unit, we could recast this as 500 terahertz, because tera is 10 to the 12th. So we divide that by 10 to the 12th. But I didn't specify a unit here, so either of those would have been fine. So make sure when you're doing these problems that you know the prefixes in that review table, table R2, which is in your book or reproduced here. Okay? So we have to know the prefixes, but if we're converting between wavelength and frequency, there's really only two parameters. You just have to solve for the one you're interested in and divide. Alright, so the reason that this is now important is because we want to start talking about what's called the quantization of energy. So this is, we're going to now talk about a few key experiments that people did where they were studying the interaction of light with matter, and it was sort of turning upside down some of the conceptions that people had about the way the world worked. So before the 20th century, everybody assumed that electromagnetic radiation and matter were two totally separate things. That you had electromagnetic radiation was made up of waves, and they had all these wave properties that we talked about, wavelength and frequency, and that matter was made up of atoms and had mass and all those things, and that there was really no crosstalk between the two, that they were two totally separate ideas. But then there were some experiments that were done that kind of made people question whether that was actually true. And so the first one we're going to talk about is black body radiation. So at this time, people thought that classical physics, the physics that Newton came up with, and then the Clerk-Maxwell stuff for electromagnetic radiation, they kind of assumed that classical physics was enough to explain the whole world. And they were kind of ready to close up shop, declare that the problem was solved and move on to better things. But then some people came out of the woodworks and did some experiments that really confused everybody. And the first one was black body radiation. So we all know what black body radiation is. If you have an electric stove, or if you use a soldering iron and things, if you heat up certain materials to a very high temperature, they glow. Okay, so that's the concept of black body radiation. It's just that a solid that's heated to a very high temperature, one that doesn't burn, of course, but I guess flames are sort of related to black body radiation. But if you heat a solid to very high temperatures, and we're talking about high temperatures, we're talking about 1,000 Kelvin, which is, 800 degrees or 700 degrees Celsius. If you heat them this high, they emit visible light, so we can see that glowing. Now this wasn't new. People have been sticking, since the Iron Age, people have been putting pieces of iron into flames and seeing them glow. They all knew that, but then what was confusing about it was that if you look at classical physics, the prediction is that, or the assumption anyway from classical physics is that matter can absorb or emit any quantity of energy. or emit, left out of order. Alright, so that's what classical physics assumed. However, if you make that assumption, it fails to explain the wavelength intensity profile of black body radiation. So in other words, if you look at black body radiation in more quantitative detail instead of just saying, ooh, look, it's pretty, it's red, but if you actually measure the wavelengths that are coming off of black body radiation and the intensity of each of those wavelengths, classical physics doesn't correctly explain that profile that you get, that relation, that trend that you get. Alright, so this was a problem here because people thought that classical physics explained the world, but it doesn't even explain something relatively simple like black body radiation. And again, the key problem was that people were assuming that energy was continuous, that the energy that came off of these black body radiations, or the energy that was radiating from the atoms, had continuous values or any possible value. But in reality, what Max Planck found out and proposed was that energy is what we call quantized into little packets. Whole number multiples of h times frequency, where h is another constant. Alright, so if you have electromagnetic radiation with a certain frequency, you can't just have any old energy value you want for that frequency. It has to be quantized as h times the frequency, little discrete, almost packets of energy. And then this was sort of baffling to people because, as I said, they assumed that matter was discontinuous, was made up of atoms, but that energy was continuous and could have any possible value. But the only way to explain black body radiation is to assume that energy is also quantized in little packets of energy that are given by the quantity h times nu. And so what this means is that the change in energy for an atom in black body radiation is given by n times h nu, where n is some sort of an integer value. One, two, three, and so on. So some multiple, some whole number multiple of h times the frequency are really the only energy changes you can have in black body radiation. H is a new constant, also on your periodic table, so don't worry about memorizing it. 6.626 times 10 to the minus 34 joules times seconds is the unit, and we call this Planck's constant in honor of the person that discovered it. Now, it's an incredibly tiny number, so in reality, these packets of energy are very small, just like atoms are very small, but you cannot have any discrete value of energy that you want. Now, in my opinion, black body radiation is the most confusing of the topics I'm going to talk about today, but it was sort of the origin of the idea of quantization of energy. I think the experiment that more clearly describes it is the photoelectric effect. And the person who studied this is someone you may have heard of, Albert Einstein. And here's sort of the description here. And this illustration shows it nicely. So if you have a metal surface, the one that's illustrated here is potassium, but you can do this for almost any metal you can think of. If you shine light on the surface of the metal, you can observe electrons being ejected. However, certain wavelengths and frequency of light, in this case the example shown is red light with 700 nanometers, if you use red light in the case of potassium, you don't see any electrons at all. And it doesn't matter how intense that red light is. You can turn up the power to, turn it up to 11, as they say. And the red light, no matter how much red light you put on this surface, you're not going to see a single electron come off of the surface. It's not until you go to lower wavelengths, green light, which would be 550 nanometers, or blue light around 400 nanometers. When you go to these higher, I keep saying higher because I want to say energy, but we're not there yet. But if we go to lower wavelengths, you start seeing electrons being ejected from the surface. And the velocity of those ejected electrons depends on the color of the light that you're shining on the surface. All right, so let's write that down in some words. So light striking a metal surface can eject electrons. But the part that was confusing people, the problem here, is that the light must have a certain threshold frequency. And if you're below this frequency, you don't see any electrons at all coming off the surface. And that's regardless of what intensity of light that you have. Alright, so this red light here, which they're not giving us the frequency, but has a lower frequency, the lowest frequency in the visible spectrum, no matter how intense the light is that hits the surface, you won't see any electrons. And then the solution that Einstein came up with was that light has discrete particles, if you want to call it that are called photons. Alright, or also that light energy is not continuous, but is also quantized into little packets of energy or particles called photons. And that the energy of the photon is given by that equation we showed earlier, h times the frequency, which can be rewritten as, once again, hc divided by lambda. So that's just rearranging using those equations. So these are two forms of the same equation. And then the other part of this was that the kinetic energy of the electron that's ejected is 1/2 mv squared. This equation I don't think you're actually going to use, but it's equal to the frequency of the photon minus h times the threshold frequency. So this is the photon that you're adding to that you're shining on the surface. This is that threshold value. And so below the threshold frequency, you don't eject any electrons. Above the threshold frequency, you're able to see electrons coming off, and they have a kinetic energy that depends on the frequency that you're using. And so this was called the photoelectric effect, and it was also then another experiment that demonstrated that light energy is quantized, it's not continuous, and that you have these little packets or particles of energy called photons, and starting to develop the idea that electromagnetic radiation and matter, there really is no distinction between them. They have both wavelength and particle properties. So I don't want to keep us late today, so we'll finish up the last concept next time that relates to this and start moving back into chemistry eventually.